All right, so last time we kind of finished our discussion on fluids, and we looked at fluids that were moving. So I just kind of want to real quick remind you, we talked about the two main types of flow. There's laminar flow and turbulent flow. So laminar follows nice paths, turbulent, it's kind of chaotic. And when it's laminar flow, we were able to do things like look at continuity and look at Bernoulli's equation and see how all this stuff was related. And so fluids are pretty interesting in terms of what we see and what we can do with them. Showed you some examples, talked about some common things that we see in the real world. But that's where we were. And today we're going to start heading into talking about oscillations. So what happens when we have things that are moving back and forth, like a mass that's bouncing on a spring or a pendulum or things like that. And basically we're setting the table for waves. So that's where we're heading, is to look at wave motion. But before we go there, any questions on stuff we've done up to this point, other than the bigger, let's talk about the exam on Friday, because we're going to carve out some time near the end of today where we can do some review. But in terms of like homework and stuff, or general comments, questions about fluids, anything out there right now?
So I went and walked at the river yesterday and watched the water. And you're totally right. Like, there's spots where it's very calm. It doesn't necessarily look like the water's moving, even though it is. And then once it narrows, it definitely speeds up.
Yeah, kind of cool, huh? That all this stuff that's theoretical, right? Because we just talked theory. We just talked about what would make sense from energy arguments and, you know, things like that. I love when you go out, even something as simple as just looking at, you know, a river or creek, you can totally see it happening. So cool. I'm glad you noticed that, Bradley. And I don't know about you guys, but I know that for me, as I learned more physics, I started seeing it, like something that we had talked about, you know, maybe the previous quarter. I would just start seeing out there. And so I live my life now all the time where, you know, I'll go for a hike out there in the meadow by the college, along the creek, and I'll see that kind of stuff. And I'll see where an eddy is forming. And I'll start thinking about all the stuff that I studied in the past with, you know, fluid dynamics. And I can't help but see it. And sometimes I even see the equations. Like, I literally, in my mind, the equations kind of pop up and all that. So, which I kind of find interesting. I know some people would say is kind of geeky, nerdy, whatever, but I think the more you see the theory and then can see in the outside world where it applies, it really helps solidify it in your, you know, in your mind, and you have a better feel for what's going on. So, but that's cool. Thanks for sharing that, Bradley. Any other questions about what we did last time?
Do you mind reviewing continuity one more time?
No, not at all. So continuity, again, is the idea that with a incompressible fluid, so water, most liquids actually are incompressible. Basically what it says is what goes in is what comes out. And specifically what that led to was looking at that velocity increase with smaller area. So let me go to the board real quick. So with continuity, it was this kind of idea. I think we drew a picture of a flow tube, but it can be whatever. But let's say that this is our flow tube. And we were looking at the volume of water, a flow rate of volume per time. And so if we were to draw, say, a little cylindrical disc here, in terms of its flow rate, we need volume per time. So volume was the area times the thickness. I think I called it ds. And then we're going to be looking at a per time. And so let me call this area 1 and then ds1. So this would be A1 times ds dt, and ds dt, of course, is a velocity. So the amount of water that's passing through this region over a given amount of time is given by area times velocity. Now, what we know is that if we go to the other end, we need to have the same volume leaving as what came in. So in this case, it's going to have to end up being probably a little bit thicker. But if we think about now this cylinder, this one, again, needs to be flowing out the same way. So it's going to have to be an A times ds over dt. The ds and the A may be different, though. It still breaks down to A times V, but now this is A2 and V2. And so continuity basically just says what goes in is what goes out, which means we can equate those two. So we get A1 V1 equals A2 V2, where A is your cross-sectional area and V is your velocity. So if you increase area, you have to decrease velocity, or vice versa. If you decrease area, then you increase velocity. And that's exactly what you were describing, Bradley, that when you went to a place that had a smaller cross-sectional area, so it was a narrower bit of the river, your A decreased, which meant you had to see an increase in your V, and it looked like it was flowing faster. As opposed to those places where it's nice and wide, you increase your A, so you slow down your V to the point where it can even look like it's not moving. So that's what the continuity was. Is that a good little review? Answer your question?
Thank you.
Yeah, okay, cool. All right, anything else? Okay, so Victor just said, how can we use buoyancy to calculate the fraction of an object that's going to float? All right, and I'm going to guess this probably came from like a homework kind of question. But when we talked about buoyancy and Archimedes' principle, we had the entirety of an object underwater or under the fluid. But with a floating object, you don't have all of it. You only have part of it. Like if you were to go out and you're playing in the lake, and you're floating on the surface, not all of you is under the water, only part of you is. And we can actually figure out what portion of you should be above or below by using Archimedes' principle. So let's take a look at this. Let's say we've got water. And then in the water, we're going to have something that's floating in it. So maybe a chunk of wood or something. But right, so we've got a chunk of wood that's floating. All right, now this is an equilibrium. So what we know is that gravity has to be countered by the buoyancy. Because if we were to actually build a force diagram for this, we're only going to see two forces. There's going to be gravity pointing down, and there's going to be buoyancy that's pushing up. Okay, so we're going to have the B has to equal G. But let's look and see, let's talk about how we calculate those. So we'll start with the gravity, because we know that one. That's really easy. That's just its mass times its gravity. But this is the mass of the object itself. And so if we wanted to calculate that, I want to relate it back to density. I'm going to call this rho dot O. So this is going to be the density of the object, so the floating object, times its volume. We'll do V dot O times G. So if you knew the volume of the object and you knew that knew its density, this is how you would calculate gravity. All right, so are we cool on that part? Yep, good. Thumbs up from Victor. Okay, so let's think about the buoyancy. All right, thanks for all the thumbs up. Good, everybody's getting it. So for buoyancy, how do we calculate buoyancy? What determines buoyancy?
It's rho times volume.
Okay, so it comes from the mass or the weight of the displaced fluid, right? So we want to look at how much fluid was actually displaced and multiply by the density of the fluid. So let's call this rho dot F, or well, no, again, it's going to be mass times gravity, but this is going to be m sub F, mass of the fluid times gravity. And so that's going to be the density of the fluid times the volume of the fluid that's displaced times gravity. So it turns out that the gravity doesn't matter. The G gravity, the gravity number acceleration goes away. And so what we get is that the density of the fluid times the volume of the fluid that's been displaced has to equal the density of the object times the volume of the object itself. All right, so the original question, Victor says, how can we use it to calculate the fraction of an object that's going to float? So really what we want to see there is what portion of the entire volume of the object is actually underwater. So that would be the ratio of these two volumes. So I'm going to go ahead and rewrite this as VF over VO, and that's going to equal rho O over rho F. So again, what this means, this VF, this is the portion that's underwater. So like if this calculated to, let's say, 1/3, so VF over VO is 1/3, 1/3 of it is underwater. If it was 1/10, 1/10 of the object is underwater, and so on. Okay, so this is the portion that's going to be underwater. And notice that it just depends on the densities of the two fluid, or the two objects, the object and the fluid. So if we're ever going to get the case where we're floating, that means that this number has to be less than 1, which means the other number has to be less than 1, which means the density of the fluid has to be greater than the density of the object. So if something's going to float, that object actually has to have a lower density than the fluid that it's in. So when you go and you float on top of the surface of the lake, it's because your body has a lower density than that of the lake. And think about this. You've probably floated on a lake, and if you've noticed what happens when you breathe in, so you feel your lungs are there, you rise a bit in the water. And then when you exhale, you sink down into the water. And that's because you're changing your density. When you breathe in, you're increasing your volume, right? You're expanding your lungs, so you're increasing your volume, but you're not really increasing your mass by much, right? Air is not very dense, so the amount of weight you actually add is pretty small. So you've increased your volume without increasing your mass, so you've decreased your density. And by changing your density, you lower this, so less of you is underwater.
That's pretty cool. I always wondered how you actually like how that works, because people would just say, I don't know, they would say something like oh, if you breathe in, you'll float like easier in the water. And so I would make assumptions like, oh, then air must float better on the water or something like that, you know, something stupid. But I never actually like figured that out. Like it's really cool that it's because of the volume that happens.
Yeah, again, we can totally explain these things that we experience just by going back to the basic definitions. I don't know if anybody in this group has ever gone scuba diving. I went one time just as a, try it out. Loved it, by the way. I can't wait to do it again. But it was really interesting that I noticed as I was down there breathing in and out, my body would kind of go up and go down. And it was entirely because I was changing the volume. Like in terms of the mass was the same, because whether it was the air was in my lungs or in my tank, right? I'm not changing the mass at all, but I was changing the volume. So we get back to the surface after this is all done, and I asked the dive master, because I noticed he didn't. He just like stayed in the same vertical spot the whole time. And I asked him, I was like, so how do you do that? Because I know that when you breathe in, it changes, your density, blah, blah, blah. I tried not to get too science geeky on him, but I'm sure it came across. But he said, well, his trick was he takes small breaths. So instead of taking, a big breath, he would just take a series of small, and he's trained himself so he doesn't get hyperventilated. Because sometimes when you breathe like that, you can get hyperventilated. But anyway, it's the real deal. So think about this. So think about like an iceberg, right? So icebergs float on water, right? We know this. In fact, that's why like the Titanic had a problem, was because the part that was underwater stuck out much further than the part that was above, right? So by the time they saw it, they ran into it, and next thing you know, Leonardo DiCaprio is dying. But let's look at how much of an iceberg is actually underwater. And we can use this formula that we just calculated. So let's go to the board. So if we look at an iceberg, what we really need to know is what is the density of the ice compared to the density of the water. And we'll even go ocean water, since usually when we think of icebergs, it's out in the ocean, although they can be in freshwater. We don't have any like glacier snow fields in Tahoe that come up to this freshwater lake, but you'll see them up in like Alaska and Canada, and I'm sure in Russia and Norway and stuff like that. But let's look at this. So if we've got an iceberg, we've got the ice in seawater. So seawater, its density, so it's going to be rho F, because it's the fluid that we're in. It's like 10, well, we'll go 1030. 1030 kilograms per cubic meter. So freshwater was 1,000, just to remind you. Freshwater is 1,000, but salt water is a little bit heavier. It's like 1,030. Okay, so I need to go back and find a density for ice. I don't know that off the top of my head. So let me see if I can find that quickly here. If not, I'll do a Google search. Okay, so ice is around 917. So the rho of our object then is 917 kilograms per cubic meter. All right, so the portion that's underwater then that's just going to be the density of our object, 917, divided by the density of our fluid, which is 1030. So if we take 917 and we divide it by 1030, I get 89% basically. This is 0.89. So think about that. Roughly 90% of the iceberg is actually underwater. You're only seeing 10% of it.
That's crazy.
That is crazy. So just think about those movies when you see a chunk of ice, just realize that that's 10% of it, or at least 10% of its mass. If you assume that the ice is fairly consistent density, then it'll be 10% of the volume as well. So if you were to change that to fresh water, so notice that this goes down to 1,000, it actually increases the underwater portion. So in fresh water, 91.7% would be underwater. There's actually less that's sticking out. And that's because its density is closer to that of the fluid. Because if the density of the object is exactly the density of the fluid, it should be right at the surface, where or if you were to stick it down even a little bit, it would just be stationary, because now this ends up being equal. So the closer you are to the density of the fluid that you're in, the more of you that's going to be under the fluid. So, but this works for gas fluids as well. Like, think about a helium balloon. You know helium balloons float, right? And in fact, they're going to raise. So think about what that means. If we're in a situation where we've got something that's floating in air, it's exactly the same story. It's just now the density of the fluid is 1 kilogram per cubic meter, which tells you that the density of helium is less than 1. In fact, it has to be significantly less than 1 to account for the extra mass of the balloon itself. So, but in that situation, then your buoyant force is actually greater than your gravitational force, and it rises. And that's the same thing like if you were to take a beach ball, an inflated beach ball, take it and put it underneath the lake, you let go and it rises, pops up to the surface. That's because its density is less than that of the water. And so the buoyant force isn't great enough to counteract, right, or the gravity, sorry, isn't great enough to counteract the buoyant force. So it goes up until enough of that balloon or that ball is out of the water, that we're in this situation again, and it floats. So think about that too. Like if you have a beach ball or any kind of an inflated ball, a soccer ball, a basketball, anything like that, when it's in water, how much of it is above the water? And I don't need a specific number.
All of it?
Yeah, just about all of it. Right? There is going to be a little bit that's underwater, but not much. So this is going to be a very, very small number. Right? Like Victor just said, like 95%. I think that'd probably be accurate. That like 95% of it's above water, which would leave only about 5% under the water. And that's basically telling you that the density of that object is only 5% of the density of the fluid.
So is that, so then the density like the first one and the second one, they're the densities of basically the fluid and of the object, right?
Correct.
Okay, I just wanted to make sure.
Yeah, so I put the little O for our object that's floating, and then the F for the fluid itself.
Oh, so fluid. Okay, that makes sense.
Oh, I see. You're thinking the F for float, maybe.
Yeah, I was thinking of like not and final.
Oh, yeah. Okay.
So I was gonna ask you, like, is there a case where you could have 2 different fluids or something? But no, that's not what it is. So.
No, but you could have that as well,
Oh.
right? You can actually have different fluids that rest on top of each other. A really good example is salad dressing.
Oh yeah.
Right? Get a salad dressing that's not creamy, but like like a balsamic or something like that, a vinaigrette that's mostly oil and vinegar with spices. And you'll notice that it separates, right? You'll get all the oil is on the top, and then the tasty part, the vinegar and all that, is down on the bottom. And you have to shake it up, right? You got to shake it up to kind of mix it. And that's because they have different densities. Oil's density is less than vinegar's. It's less than water's. That's why oil floats on water. So if there's an oil spill, it all ends up at the top of the water surface.
That's interesting.
Yeah. So again, a little bit of knowledge now really explains a lot of what you see. So, but to get back to your question, Victor, did that pretty much answer it? Are you good? Yep. Okay, cool. All right. Anything else about fluids? No? All right. Obviously, if other questions come up, please feel free to ask.
So I have one.
Okay.
Life as we know it on Earth could not have, well, I shouldn't start there. Life on Earth as we know it would be totally different, possibly, if ice was denser than water.
Oh, absolutely. Yeah. There are so many things that life as we know it depends upon physically. And yeah, that if water's density was different and like compared to ice, yeah, all kinds of weird stuff would happen. Instead of like the ice forming on the surface of a lake, like it would form on the surface of the lake probably because it cooled, but then it would sink down to the bottom. And then the next set would freeze and sink, freeze and sink, freeze and sink, until eventually it would all become ice. Where as we have it right now, you can get that ice formed on top and it stays there and it stays liquid underneath. Like in the winter, fish just keep doing their thing. They don't even notice that it's wintertime. You know, that's why people can go ice fishing like in Minnesota and all that, where they're sitting on top of the ice, they drill down in and they can still fish. But yeah, it'd be weird if ice was more dense than water, which in general is odd, that a solid of a material is less dense than the liquid of it, right? Because usually solids tend to sink, but actually no, I think that's probably true, because I just started thinking if I had liquid gold and I put solid gold in it, I think it would probably float until it melted. I have to think about that. But yeah, it would definitely be different if that were to occur. I thought you were going to go with gravity was different, but that also would change things immensely. Like imagine if gravity was greater, we probably would be shorter because it'd be harder to, say, pump blood up. Like when we were talking about fluids, I didn't even go there, but I want you to think about like a giraffe. And so a giraffe has a fairly large vertical difference between, say, its heart and its brain. And that fluid has to flow up there. And we already saw from Bernoulli's equation that elevation matters. So there has to be a fairly strong pumping mechanism to get the blood up there. So giraffes are kind of unique. There are not a lot of animals that have like really long necks like that. There are a couple like birds, there's like the emu and stuff like that. But in general, we don't have huge vertical separation from heart to brain. And part of that is to deal with the pressure differential needed to make fluids move. So if gravity was greater, that would be even a bigger of an issue, because you may remember in that part of Bernoulli's equation, there's the G that's being multiplied to the Y, to the difference. So yeah, if we were on a heavier gravity planet, animals would probably be stockier. They wouldn't be as tall. Obviously, there would still be exceptions, but yeah, all kinds of fun things to think about. What would happen to life if we change certain physical parameters? So anyway, good questions. I love it. I love it when you guys ask me stuff about this, because it shows you're thinking, it shows you're interested, and I definitely appreciate that, because it is pretty damn cool.
I do agree that it's really cool to see physics like in real life, and I agree also that kind of like when once you start to understand it, you start to see it more in physics terms than just life.
Yep.
And I think that's really interesting.
Yeah, and when you guys start getting there, that's when you know you're in it, right?
Yeah,
You're
yeah.
really in it when you start seeing it. So for those of you that are starting to see it, cool. That means you're turning that corner and realize that you never go back. You never go
Yeah,
back.
I'm okay with that.
Like
We're selling our souls to the physics.
Yep. So this comes up all the time when I'm talking optics. I am the worst. I ruin so much magic when I talk about optics. Like I tell you exactly why rainbows are formed, and the next thing you know, you can't be like, oh yeah, the pot of gold and the leprechauns and the no, it's all gone. So you lose all those fantasies, but you replace it with reality, which I think is probably better. So, but that's personal opinion.
Yeah.
Anyway. All right, well, hey, let's talk harmonic motion now. Let's talk about what happens when things oscillate. So basically what we're talking about, I brought in one of the many things that I stole from the lab on my journeys into the college, is I basically just have a spring here. Let me move this out of the way. So I've got a spring, and you notice it's just got a little thing on the end so that it can hold mass. And I'm going to put a little mass on it. Not a lot. I'm going to add 10 grams to it just so that it stretches a little bit. Makes it a little more sturdy. But if I pull it down and I let it go, let's see if I can get it without going sideways. If I pull it down and I let it go, you see that it just goes up and down. Right? So it's just bouncing up and down, up and down, up and down. And it's going to continue to bounce up and down until eventually it will stop. And the reason that it's stopping is because of air resistance, friction, right, drag, that kind of stuff. So it'll eventually stop. But in the absence of that, if we had no loss due to friction, this thing would just continue bouncing up and down forever. So this is what we call simple harmonic motion. Any type of object where we have, or any type of situation where we have an object that's oscillating between two positions. Okay, so springs are an example of simple harmonic motion. Another example is a pendulum. So let me just, I got my wireless earphones here, but you notice I've got the power pack kind of dangling here. I can do the same thing where I can displace it a little bit. So I'm going to displace it a little bit here to the right, my right, your left, and I let it go. And it's just going to oscillate back and forth. Now, it's a different kind of oscillation. A different thing is driving it, because it's not a spring anymore, right? It's a pendulum, but it's still going back and forth from two positions, right? It's going from my finger here on the right over to my finger on the left. It might help if I don't hit it. But it's bouncing back and forth between those positions. So a pendulum's another example of simple harmonic motion. And simple harmonic motion can take all kinds of forms, just as long as we have something that's going back and forth between two positions. But we can actually describe it a little bit better than that, because there are lots of ways you can go back and forth. But for both of these, it was really regular, right? It was very predictable, very regular. It wasn't like the spring was doing this kind of deal, right? And the pendulum wasn't doing a loop and coming back. I mean, it was just very regular, very predictable. So let's define it a little bit better. Let me go to the board. So simple harmonic motion, the way that we actually define this, it's going to be where your acceleration is proportional to your position. So from henceforth, this is going to be SHM, by the way. because I don't want to have to write that whole thing. But in simple harmonic motion, the key is that your acceleration is proportional to your position. So basically what this means is that the farther away you are from zero, whatever zero happens to be, and we'll talk about that for the different scenarios, but the further you are from zero, the more acceleration you're going to feel. So that's what this says. But there's also another piece to this, and that is that this acceleration is always pointing in the opposite direction of motion. So I'm just going to put here opposite of position. So if we're in the positive, acceleration is pointing in a negative direction. If we're located at a negative, then acceleration is pointing positive, and so on. So let me show you with the spring how this is set up. So we had the spring, and on it was the mass. So let's just say 0 is where it would be if we don't pull it down or push it up, when it's just stationary. So let me just show you again real quick on the other screen, because I think you can see the spring better here. Okay, so here is the spring again. So 0 for the spring would be at this level right here. Okay, because that's where it is if I don't pull it down or anything. And let's go with positive being up and negative being down. So think about this. If I pull it down, it's now in a negative location. So for simple harmonic motion, acceleration has to be pointing positively. So in this case, up. And that's exactly what's going to happen. This is going to accelerate upward, right? But now if I get beyond 0, so now I'm up here, it's going to want to fall back down because now the spring force isn't great enough to maintain it. So we're in a positive position, but our acceleration, because it's mostly gravity, is going to be pulling down. So that's what it would look like in that case. In the pendulum case, as this is going back and forth, same kind of deal. Positive would be, say, to the right, negative would be to the left. When we're up here in the left, it wants to move to the right and vice versa. So this is technically what we mean for simple harmonic motion. Okay, so easy enough. Well, it turns out that that's enough for us to figure out what sort of form our position function needs to be. So let's do some math. All right, so if we look at this, where the acceleration is proportional to position, so what I'm going to have then is acceleration. It's going to be proportional to position, so we'll use x for position. But this isn't quite enough. It actually has to be a negative times that, because it needs to point in the opposite direction, remember. Okay, so the question is, what sort of an equation is going to give us this? Actually, let me change this from K, because with springs, K means something, and I don't want to go there. I just want to go something. All right, well, let's think about A. Acceleration is related to position. It's actually the second derivative. So what we're seeing here is the second derivative of position is going to equal this negative cx. Now, most of you have no idea how to solve this equation. This is a differential equation. You have seen some differential equations. I don't know that you've ever seen what we call a second order. but there is one of you who has seen these. And in fact, Ian, I want you to look at that and recognize that that's exactly what we were talking about today.
Yep.
This is a linear second order homogeneous with constant coefficients. So for all of you but Ian, just watch this and smile and nod. But I want to show this to Ian just to really reinforce why we care about stuff like we talked about today. Okay, so we create the polynomial. In this case, that characteristic polynomial is going to look like r squared plus c equals 0. So then think about solving that. This is going to give you r equals plus or minus the square root of negative c, which means we have complex roots. So what form do we take on if it's complex? Do you remember, Ian? And I'm totally putting him on the spot.
Wait, yeah. Wasn't it it was the third case, so it was the cosine and sine of the
Yep.
BT.
It was cosine and sine. So what we know, and you notice there's no real part, so there's no exponential bit. So what we're going to get for our position x, it's going to be some combination of sine and cosine. So I'm going to put here cosine and or sine. Okay, so for the rest of you, you'll learn how to solve this next year. But you actually already could have kind of figured it out. Think about it. What kind of functions, when you differentiate twice, give you the opposites of what you just started with?
Trig functions, but I also remember something you said in trig, that you said the sine and cosine functions are oscillations.
Okay, yeah, I definitely talk about that in trig as a reason for why we do trig. But you can definitely see it. Think about sine. Its derivative is cosine, whose derivative is negative sine. So negative sine is a negative multiple of that guy, right? So you can see that sine and cosine work as well. So we actually can use either one, but the one that I'm going to use, because I think it fits a little bit better, is I'm going to use cosine. Okay, so let's think about what cosine looks like in generic cosine. So we're going to have x equals a cosine of, I'm just going to put here, say b times t. Another letter that we used here, I don't know if you remember, was that guy omega. So just in case, that's the one that you saw. That's the one I tend to use. I use omega for that. But this would be your generic graph of cosine. And this actually works really, really well, especially for when we want to start with maximum displacement, right? Because remember, cosine starts at a maximum. So if we want our position to be furthest from 0, this is the perfect function to use. And if you think about both examples I just showed you, both the pendulum and the spring, I started by pulling that spring down all the way so I had maximum displacement. Or I took that pendulum and I moved it all the way to one side and then let it go, right? So it was furthest away. So in lots of applications, we want to start with maximum displacement, which is why it's great to use cosine. But you can use sine just as well. You just have to phase shift it. We don't want to phase shift if we can avoid it. All right, so when we have something in simple harmonic motion, it actually follows a sinusoidal wave. And we're going to go ahead and use cosine. So check this out. If we go back to that original differential equation, let's look at what that C ends up being, right? We have x prime is equal to minus omega A times the sine of omega t. That omega comes from the chain rule. And then x double prime, that's going to be minus omega squared A times the cosine of omega t. And so if you look at these two, the position and the acceleration, you notice that acceleration is a multiple of position. And what we see, if we go back to that, how I had it written as x double prime equals c times x, or I guess minus c times x, this tells me that c is actually equal to omega squared. So that constant, that proportionality constant, is actually equal to omega squared, whatever that ends up being. Okay, so cool. We have a solution. We know that simple harmonic motion is going to follow a sine, which is exactly why, like Bradley said in trig, I mentioned that this was a case of where we use sine and cosine. All right, so while we're talking trig, let's just remind ourselves some things. What is the A? What do we call that A? Or more to the point,
amplitude.
Yeah, the absolute value of it. That's the amplitude. And so amplitude just tells you how far your position varies, like the limits on your position. So if we have a spring and I pull it really far down, so I take it and I pull really far, I'm going to have a much larger amplitude than if I start with it and just pull a little bit. Right? So that's what's going on there. That's the amplitude. And then what is the omega? Remember what that is?
It's phase shift.
Actually, it's not the phase shift. And Victor, you're right. It modifies the period. It changes the period. It's not the period itself, but it's related to the period. But this guy, omega, this is the same omega that we saw with rotation. It's an angular frequency. Now, that doesn't really make sense when we're talking about, say, like a spring. You're going to look at that and go, oh, there's no angle anything. But because we're using the trig functions to describe it, we do have angular frequency. But if you remember, this is related to the period by 2 pi over the period. So this guy omega, it actually equals 2 pi over the period. So that's how we're actually going to figure out what omega to use, is we're going to look at the period. How long does it take for that pendulum to go all the way over and back? How long does it take for that mass on the spring to go all the way down and back, right? So that's going to determine our period, which then will give us our omega. We don't really use a letter for period when we're doing it in trig, but just so you guys know, the period we're going to use the letter T, but a capital T. So big T is going to be the period, as opposed to little t for time. But you can see why we use big T, because period is a length of time, but we use the capital instead of the lowercase just to differentiate it. All right, so there's our period. And then one other thing I want to mention is frequency, because this was angular frequency, but regular old frequency, when we talk about frequency, this is how many times something occurs. So we use the letter F for this, and it's actually just 1 over the period. So you're probably familiar with that, but in case you're not, we use this guy F. It's going to be 1 per period, so 1 over T. So the units on frequency, these are seconds to the -1. And that's such a common unit measurement that we give a name to it, and that's what we call a hertz. So 1 hertz, and it's just like the car rental company. 1 hertz equals 1 second to the minus 1. And we don't ever write out hertz. We write capital H with a Z, lowercase z below it.
Is that what they use in music?
That is exactly what they use in music. So when they talk about a frequency that's a certain number of hertz, or radio stations, their frequencies are in megahertz and so on. But yep, it's
I see.
all about the frequency. So basically they're telling you how often the wave cycles, and then you can use that to actually figure out what the period is by just doing 1 over. Yeah, Max, you'll see the tie to all this oscillation stuff to music in a little bit. A little bit meaning a couple of days.
Okay.
Okay, so we'll get there. We'll talk about where we use this. Okay, so then the one other thing that can be in there is a phase shift. And the phase shift just allows us to not start with a max. And do you remember where the phase shift is in the equation? Because you would have seen this in trig. All right, so Victor says it's inside. Yeah, it's inside the trig function. So if we want to allow for a phase shift, we'll actually write it generically as A cosine omega t plus phi. So we're adding a constant inside there, and that constant will help determine what the phase shift is. And again, just to remind you, because it may have been a while, the way you calculate a phase shift, it's going to equal phi over omega. So that tells you how far it's been shifted. So if our maximum isn't at time 0, but somewhere else, we figure out where that is. That's our phase shift. And then we can set that equal to phi over omega to actually calculate the phase shift. So you can see why, to Bradley's point, when I brought this up in trig, you can see why I did. Because it's a really good example of where we have to use amplitudes and periods and phase shifts. So I gave you an example of spring, but it could have been anything that oscillates, including a pendulum or anything else. All right, so how we feeling so far? Not too bad?
Pretty good.
Pretty good? Okay. Notice that if we do throw in a phase shift, it doesn't change anything with the derivative because we're just adding a constant that doesn't go away. So we still find that that proportionality constant is omega squared. And so, and then the same thing with the velocity. The velocity is still going to have the minus a omega sign. Right? So the phi doesn't actually do anything there. All right, so this is simple harmonic motion in general. So let's look at a spring. Let's see what about the spring determines all of this. All right, so let's just go back to the basics with springs. So let's start with good old force. What's the force due to a spring? You remember the formula for it? Hooke's law?
Negative kx, I think.
Good. It's negative kx. So k is the spring constant. It's a measure of how stiff or stretchy the spring is. The force, it's dependent upon how far away we are. And it's always opposite direction. So if we go to Newton's first law, or second law, sorry, we have m times a equals minus k times x. Let me write that over here. which means if we solve it for A, we get A is equal to negative K over M times X. And this right here is enough to show you that it has to be simple harmonic motion. Because remember what we wrote? We wrote that A was equal to minus C times X. Well, now the C is K over M. All right, well, even better, we can figure out what the omega is. So when we did that whole deriving the differential equation and everything, we ended up seeing that omega squared was equal to this constant. So for the spring, we've got omega squared equals K over M. So omega is the square root of K over M. So what that means is that we actually have a position function now for the spring. It's going to be x equals A, which is going to be determined by how far we've moved it, how far we're deforming it, times the cosine of the square root of K over M times T. So Bradley, I think you were about to ask me a question, but I talked over you.
Oh yeah, you're good. What does that say on top? Springs and sweat strings?
SHM, simple harmonic motion.
Oh, okay. All right, thank you.
You're welcome. Make it a little more clear. So back when you did springs with Kathy, I doubt you went here unless she just gave you the formula, right? There's no way you actually derived it at the time. But there it is. There's the position of a spring at any given time. Again, A is going to be how far we're moving it from the 0 mark. And then if you want to figure out how fast it's oscillating, we got it here. So this is our angular velocity, or angular frequency, which means we could still go ahead and find the period, and we can actually find the frequency as well, right? The period, remember that this guy omega is 2 pi over the period. So the period is going to equal 2 pi divided by omega, which is going to be 2 pi times the square root of m over k. Now, I want you to think about how powerful this is. Because this right here, remember, period is how long it takes to complete a cycle. So this would be if we were going to time our spring from the bottom up and back down. That's big T. That's the period. So we could take a stopwatch, calculate that. If we know what kind of mass we're hanging, we can use that to figure out K. So this is an alternative way of figuring out your spring constant. Alternatively, if you know the spring constant and you know what mass you're hanging, you can immediately figure out what your period should be. So that's your period. And then of course the frequency is just a reciprocal of that. So it would be 1 over 2 pi times the square root of K over M. But we now know everything about what happens with a spring when it's going through simple harmonic motion. Yes, there's still the, well, what about the reality where there is air resistance and we do lose energy? Nah, we'll get to that later. All right, so how are we feeling? Not too bad?
Yeah.
Yeah?
So I have a question for you.
Go, Bradley.
I'm assuming when I ask this that the rotation, like suppose you have a sphere and you rotate it, eventually it'll oscillate, like how the Earth does around its pole. You know how the Earth has oscillations? Is that simple harmonic motion?
So yes, rotation and simple harmonic motion. Rotation is simple harmonic motion. Yeah.
Okay.
We'll get there. It will be example number 3. Example number 2 is going to be the pendulum. All right. So let's look at energy now. Let's use this idea with the spring to look at energy in the spring, because then we can take those ideas and expand it to anything in simple harmonic motion. All right. So let's look at the energy in a spring. To help us out, I'm going to look at this horizontally instead of vertically, because I want to eliminate gravity, not having to worry about gravity, potential energy, and all that. I want to look at just potential energy in a spring. So let's turn this sideways. So we're going to have our spring, and it's going to be attached to some sort of a block. And let's say that this is neutral position, so this is going to be 0. Okay, so this is going to be x equals 0. Now, if we're in this situation, how much potential energy is in this system?
K.
So K?
Mm-hmm.
I would say 0, right?
Why do you say 0?
Because if it's at the origin, it's not really like charging any energy. I don't know if that makes any sense.
Not really. I mean, I think I might know what you mean. Well, let's just think about this. So we're talking about potential energy of the spring mass system. So it has to be energy in the spring. Now, if the spring is compressed, there's stored energy. Because if I let go, it's going to want to expand. Same thing if I stretch it, there's stored energy, because if I let go, it's going to want to come back.
Yeah, I think that's what I was trying to get at, I think.
Okay. And if you look at what Victor wrote in the chat, he just says it's in the original position, so there's no force acting on it. And that's true. When it's at the equilibrium position, this is where the spring wants to be, there isn't any potential energy from the spring. That's why I'm not doing this vertically, because I don't want to worry about gravitational potential energy. But as soon as I move it one way or the other, we start getting potential energy. So let's see if we can figure out how much that is. And obviously it's going to depend on x. All right, well, let's just go back to how we calculate potential energy. We look at the work, right? What's the work done? So let's look at the work done as we go from some position. Let's just say that this is x initial to x final. Okay, so we're going to, not necessarily at 0, but we're going to be somewhere. But we're going to pull on it to lengthen it out. And I want to find out how much work happens with the spring, because then we know we can use that to figure out the change in the potential energy. So the way we calculate work is it's the integral from wherever we start to wherever we end of the force. And we know in the case of a spring, this force is going to equal negative kx. So that one we can do pretty easily. So this is going to be minus kx squared over 2 at x initial, x final, which gives us 1/2 k. I'm just going to pull that out because it's a constant. So 1/2 k times, and it'll be x initial squared minus x final squared, because this minus sign out front switches them. So this right here is the change in the potential energy. All right, so now let's go back to the, what is it going to be when we're somewhere? Well, let's start with x initial being 0. Because if we let x initial equal 0, we know what our potential energy is there. It's 0. So whatever potential energy we get once we stretch it, that's going to be the total difference. That's going to be the total change. And let's just call x final x. We don't need a separate letter for it. All right, so this has to be our change in potential energy. So if we put this stuff in, we're going to get minus 1/2 kx squared but you should probably not like that. What about that doesn't really work so well? Or maybe you do like it, I don't know. I have a problem with it.
Yeah, what Victor said, the negative.
Yeah. So the negative, that's suggesting that we actually have less potential energy when we're further away. Ugh. Okay, well, here's the deal. When we come back and we look at this, I kind of tricked you a little bit by putting that minus sign through. If I hadn't put that minus sign through, if I put that minus here, this would have been x final minus x initial, which means that this is actually the negative change in the potential energy. Because when we do potential energy changes, we always look at final minus initial. So this is actually negative du. Which then the signs turn out exactly what we need. All right, so what that just told us, what we just figured out, is that the potential energy that's stored in a spring is 1/2 kx squared. I actually wouldn't be surprised if you guys did calculate this back when you did springs in the first quarter.
We did.
So you did, all right.
Mm-hmm.
So you've seen that. So then you probably know where the kinetic energy is. How does kinetic energy work on this? Where does it have maximum kinetic energy and where does it have minimum kinetic energy?
I think maximum is at the center.
Yep, it's got greatest kinetic energy when we're in the center, and it's got the least when we're out at the extremes. Because for that instant, we've actually dropped our velocity to 0. All right, well, let's look at the total energy. So, because we've got this, and then of course kinetic energy, it's 1/2 mv squared. So we don't need to rederive that or anything. It's still the same if it's a block on a spring or anything else. So let's look at total energy. So total energy is going to be the sum of these. Now what I'm going to do is I'm actually going to put in our x and our v from simple harmonic motion. So we know that x was a cosine of omega t plus phi. So that's our 1/2 kx squared. And then for our mass bit, we're going to have 1/2 m. And then the velocity, that's a minus omega a sine. And I'm sorry, I ran a space there. But that's just going to be a minus omega a sine.
Why is it negative?
The derivative of cosine is negative sine.
I see.
Yep.
Because it's velocity, not acceleration.
Correct.
Okay.
All right, so let me do some algebra on this. So we're going to get 1/2 ka squared cosine squared. This next piece, we're going to get plus 1/2 m omega squared a squared sine squared. But I'm going to replace that omega squared. Hopefully you remember not that long ago we saw that omega was the square root of k over m. So omega squared, this is going to equal k over m. So the m's are going to cancel, leaving behind just the k. So we've got that the energy is 1/2 ka squared cosine squared omega t plus phi plus 1/2 ka squared sine squared omega t plus phi. And now we get to use our favorite trig identity of all time. Notice that if I pull out that 1/2 ka squared, factor that out, I get cosine squared plus sine squared, which of course is just equal to 1.
Crazy.
It's totally crazy. Look at the 3 things that I've boxed.
It really simplifies it so much.
It does. And look at all those forms.
Yeah.
1/2 something times something else squared. Every single one of them. It's almost magic. But I think this is why we call it simple harmonic motion, because it does actually simplify down really, really well. So what's in the black box, that's our total stack of cache, right? That's our energy cache. That's how much energy we have to distribute. And we constantly just keep swapping it from a pile of potential and kinetic. So not only do we now know that, greatest potential energy is when we're furthest away and greatest kinetic is at 0 and all that, we know what the maximum potential energy is. It's going to be 1/2 ka squared. But that makes sense because a is how far we're stretching out. which is going to be our maximum x. But it's really being able to link this to the kinetic energy, because then we can figure out exactly how fast we're moving at our greatest. So check this out. If we look at V max, the V max is going to be when 1/2 mv squared is equal to 1/2 ka squared. So we get V max squared is equal to k over m times a squared, which gives us V max equals the square root of km times a. But even this isn't really surprising, because this is actually the same as omega a. And if you go back and you look at our velocity function, when we differentiated it, let me write it again up here on the very top. If we went with a is equal to cosine, or sorry, x is equal to a cosine of omega t plus v, we get that v is equal to negative omega a sine of omega t plus v. So think about this. When is this maximum? Well, it's going to be greatest when sine is plus or minus 1, which gives us a velocity of either negative omega a or positive omega a, which is exactly what we found down here. So it's good to see that all of this works no matter which approach we take. And hopefully you're very convinced that cosine is the function that we can use to describe simple harmonic motion. Because if you're not convinced at this point, I don't know how to convince you, saying everything just sort of works together. All right, well, let's take a break. Let me go ahead and pause here real quick. All right, so now that we've seen that springs definitely follow simple harmonic motion, let's go to pendulums. Let's talk about why we get the same thing, excuse me, with pendulums, and then how it's going to determine, or then the fact that it is simple harmonic motion, then we know everything about energy and all that as well. So let's go to the board and let's take a look at force diagram for a pendulum. All right. So let's say we've got a pendulum, and we're going to do what's called a simple pendulum. So a simple pendulum, that just means that the string or whatever it is that's holding it up is very, very low mass, so virtually no mass, and there's going to be no friction, no air resistance, no energy loss for any of those reasons. So here's our picture. So we're going to have some sort of mass hanging off of a string. Let's draw some other stuff here. Let's go with the vertical position. So this would be neutral. This would be 0 in terms of everything. So if we are in that spot, there'd be no potential energy or anything like that. All right, so what forces act on this? All right, Victor just gave me gravity. I think the rest of you guys are just so lazy now, and you're like, ah, Victor will say gravity. So, all right, so we definitely have gravity. What else? All right, thanks, Ralph. Also the tension. So we've got gravity pointing down, we've got tension pointing up. And that's it. So we've got tension and we've got gravity. Now, what I want to do is I want to change this so that we've got a coordinate system that's in line with our string. So one of the axes in line with our string, and the other one perpendicular to it. So that would be tangent to the path. So I want this to be my coordinate system. So that means I need to break down that gravity into its two component pieces. So it's going to break, excuse me, it's going to break into a portion that points this direction and a portion that points that direction. Let me give an angle here. Let's just say that this angle is theta. So if that angle is theta, then this angle is theta, which means I can break the components down pretty easily. They're going to be mg cosine and mg sine, respectively. So this one is going to be mg sine theta. And then the other one's going to be mg cosine theta. All right, so this is nothing new. You've seen this sort of picture bunches of times up to this point. Okay, but now what we're going to do is we're going to think about the torque on this system. Because what wants to happen is that this pendulum wants to rotate in a circle. It wants to rotate. So thinking about that, what's actually providing the torque here?
Gravity?
It is the gravity. The tension's not performing anything. It's only the gravity. So when we go and we look at torque, the torque, remember it's the radial arm. It's the distance away. So let's maybe put a letter here. Let's use L for length of our pendulum. So we need to take the distance away times the gravity, so m times g, times the angle in between them. And you can actually see why it always ends up giving us the sine of the angle in between them. That's the portion that's actually causing the torque. That mg sine theta is actually perpendicular to the radial arm. So there's our torque. All right, so we'll go ahead and call this positive torque for right now. We'll go with the usual counterclockwise is positive. So this is trying to move in a clockwise direction. All right, well, let's replace torque. Using Newton's second law, the rotational form, this is I times alpha equals L times mg sine of theta. And now we'll put in for our moment of inertia. Since we're assuming this is simple, we don't have to worry about the moment of inertia of the string or anything. It's only the mass. So we don't even have to go to sphere, Victor. We can just assume that it's a point mass. So that makes it even easier. That makes it just ml squared. So now let's solve this for alpha. So we do a little algebra on it. The L's cancel. Well, one of the L's cancel, as does the M. And we get alpha is equal to G over L times the sine of theta. So moment of inertia is always mr squared for point masses. The r, we're just designating it as L. Sorry about that. All right. Now, notice that this is not negative. It's actually positive, but it is opposite of displacement. If we think about being vertical as 0, since I moved in a clockwise direction, I've got a negative angle, which is giving me positive acceleration. So I've got my opposite signs like I want. If I had gone to the other side, so I rotated clockwise, or sorry, counterclockwise, that's a positive theta. We'd see that our alpha is negative because it's trying to rotate us in a clockwise direction. So we definitely have the setup where our acceleration is pointing in the opposite direction. But there's a bit of a problem in that our acceleration isn't proportional to the angle, but it's proportional to the sine of the angle. Well, have no fear. We have a way of dealing with this, and it's that good old small angle approximation. So I know I've talked about this before. Remember the small angle approximation? It says that if your angles are small, like I think the max where it's good to assume it is like 15-ish degrees. As long as you're under that, this is a good assumption. The small angle approximation says that the sine of theta is almost the same as theta. So if we use that, then we're going to get alpha equals G over L. And I'm actually going to put a negative theta because of the fact that we went in a negative direction for this. And now you can totally see that this is the exact same structure as what we saw for the spring. We've got alpha is equal to negative G over L theta. So this is theta double prime equals minus G over L times theta. It's got a different constant, right? If you go back and you look at the spring one was involving M and K. Well, for pendulums, it involves G and L. So by a similar argument as what we did last time, you can see that omega then is equal to the square root of G over L. So pendulums are simple harmonic motion, which means they behave very much like springs, which I think is kind of cool. Two completely different structures, and yet mathematically they behave the same way. But now it's not mass and spring constant that matter, it's gravity and the length of our pendulum. Right, so you can use this to figure out period, you can figure out frequency, right? So like period, remember it's 2 pi over omega. So the period in this case is going to be 2 pi times the square root of L over G. So Victor just put here, so alpha doesn't depend on mass. Yep. And that's kind of weird, huh? It seems like the amount of mass that's hanging off the end of the pendulum should affect how fast it rotates, or not how fast it rotates. Well, yeah, I mean, omega. It doesn't actually affect it. What it does change is the tension that's on the string, because the tension is equal to mg cosine theta. So if you had something really heavy, you'd have to worry about the string breaking. But the period is going to be the same, whether it's a kilogram or 100 kilograms or a gram, if it's simple harmonic, if it's a simple pendulum. Obviously, things will be a little bit different when we take into account air resistance, because drag will affect it. how much drag will change depending on the size of the object, but we're not there yet. So yeah, and I agree. It is kind of cool, Victor, that the mass is irrelevant in this case. You want to time a pendulum, mass doesn't matter, only length. Now, in the real world, we don't have a simple pendulum. We do have to worry about like the mass of the rod and things like that. That will affect things. But in this real basic kind of scenario, yeah, that's all there is to it. All right, so another example that's going to lead to simple harmonic motion because we get the same differential equation, or at least the same structure of a differential equation. So in terms of the form of the equation, it's the same kind of deal. It's still going to be an A cosine of omega t plus phi. The A, now that's an angle. Because remember what we're doing, we're getting a theta equals for this function. So your amplitude is the greatest angle away you are. So if we pull that pendulum over and we let it go, we have to know what the angle is, not the horizontal distance, but the angle that we rotated through. So that's what A is. It's the maximum angle of displacement. And then your omega, again, depends on G and L. All right, so cool. All right. So there you go. There's a second example of where we use simple harmonic motion. So the third one is rotation. Rotation is actually also an example of simple harmonic motion. And let me show you why. So here's what we're going to do. We're going to have something spinning in a circle. And we're going to be shining a light. Okay, so this is all light. Chandelier or something, right? So all that light is coming down. And so this particle that's on the circle, it's going to be creating a shadow down on the table. Let's just think about that. And what I want you to do is think about that shadow. So if we're starting right here, you see that shadow located directly below. So it looks like that. Now, as this rotates in a circle, and we'll go in a positive angle direction like we're used to for counterclockwise, think about what happens to that shadow. That shadow is going to start out here, but then it's going to move. And it's going to continue moving until it reaches over here and gets to as far away as it possibly can. So if we kind of follow what happened, it went like this. What's going to happen as it continues to rotate?
It's going to appear to go backwards.
Yeah, that shadow is going to move in the opposite direction, and then it's going to move this direction and this direction and so on. So it's going to look like it's just bouncing back and forth. Just going back and forth, back and forth, back and forth, back and forth. Okay. That's sounding a lot like what we talked about, springs oscillating back and forth, pendulums going back and forth. But what we need to guarantee that it is simple harmonic motion is to see that its acceleration is negatively proportional to the position. So let's just think about the location of the shadow. So let me give you some coordinates. Let's just say that right here, smack dab the middle, that's x equals 0. Okay, well, I think you're seeing where this is going. This x, it's just equal to the cosine of theta, where theta is whatever angle we need from the standard position to get there. This was unit circle definition. Go back to trig 101, right? Like day 2 maybe of trig. All right, well, obviously theta changes with time. And the way theta changes with time, you know that d theta is equal to d, or d theta dt is equal to omega. So d theta is equal to omega dt. And if I integrate that with respect to t, I get theta equals omega t. So now this looks like x equals cosine of omega t. And that, my friends, shows you that this is simple harmonic motion, because its derivative, or its second derivative, I should say, so its acceleration, is going to actually be equal to the negative omega squared times this original position. And I did this horizontally, but you're going to see the same thing vertically. Right? Like if we were shining light from the side, you'd see the same thing happening over here, that you're seeing that shadow bounce back and forth. And in that case, we'd be using the y coordinates. But y is equal to sine of theta, so it's going to be sine of omega t. And we already saw sine or cosine doesn't really matter because the derivatives are such that it still gives us the acceleration being negatively proportional to the position. So I don't remember the context of that question earlier, Bradley. You said something about going in a circle, but going in a circle is definitely simple harmonic motion.
Yeah, I was specifically when I asked, I was thinking about the rotation of the Earth and how it oscillates over time.
So are you talking about like the wobble?
Yeah.
Because, so like, and make sure I'm interpreting this right for what you mean. But when yeah, I got my Earth here, right? So when you have something like the Earth spinning, it spins around the axis, right? And for the Earth, our axis is off at 23.5 degrees. That's what gives us seasons. Okay, but what also happens is that this axis doesn't stay fixed. It wobbles like that. So is that what you were talking about, Bradley? Just want to make sure.
Exactly, yeah.
Okay. So this isn't exactly due to simple harmonic motion. You can actually describe it with simple harmonic motion. But this is just something that happens with spinning things, is that if that axis isn't, or it's really if the mass distribution isn't perfect, then it will start to spin a little bit out of control. Like think about if you ever played with a top as a kid, right? And when it's spinning nice and fast, it doesn't really wobble much. As it slows down, it starts to wobble more. It's a conservation of angular momentum thing, actually. So, but there's definitely harmonic motion when it comes to rotation. And so the Earth experiences simple harmonic motion multiple ways, except for the fact that we don't actually travel on a circle, but close enough. Right?
Okay.
All right. So cool.
Yeah.
All right. Other questions on the circular motion? Does it make sense how going in a circle is really the same as doing simple harmonic motion? So again, I find this interesting. 3 completely different things. Completely. And yet they all are described the same mathematically. So to a math guy, really to a math guy, I'm like, bah, they're all the same thing. Just like I can say circles are triangles. Obviously they're not, but to a mathematician, sure, they're the same. These 3 things are the same. Yeah, I think I finally have convinced many of you that circles and triangles really are the same.
I told my buddy that, and he's like, "No, they're not." I'm like, "They are, though," and I proved it to him with basically using a unit circle with radius 1 and the equation of a circle. And by the time I was done showing him, he was like, "Man, fuck you! It's not the same thing."
Well, I can't tell you how proud that just made me. By the way, Bradley, thank you so much for becoming a disciple and becoming a missionary, actually, in the circles and triangles are the same thing religion, because that's what it's going to take for it to catch on. But yeah, no, that's awesome. That makes me happy. All right. So, but let's talk reality. Let's talk reality, because when I take that spring and I let it go, it doesn't follow simple harmonic motion. It eventually dies off, right? We eventually see it cease to oscillate, right? And that's because it's getting slowed down. It's losing energy because of friction. And what we call that is a damped oscillation. So when something is damped, it's being shrunk or retarded. And so damped harmonic motion is one where we're actually losing amplitude. We're losing amplitude as we go. And it's because it's just energy loss for whatever reason. On Earth, most of it is air resistance. But even if we set that same thing up on the moon, it would still lose energy because of the spring being deformed, some friction where the spring is attached to the surface, things like that. Just in our world, air resistance tends to be the biggest. Okay, so we can dampen this motion. We can also assist it, right? Like think about that spring as it's bouncing up and down. What if I just regularly tapped it? And I just timed it so every time I was tapping, I was hitting it right when it was at its max, right? So think about that. I'm actually aiding it. So I'm not dampening it. I'm actually aiding it. And so we can do that as well. But that's called a forced oscillation. So you can have damped oscillations, you can have forced oscillations, and they each behave a little bit differently. Now let me just kind of give you the nuts and bolts of what they look like. So in terms of the math, I'm not going to go super far into this because you need differential equations. This is another one I'm going to just tell Ian. Watching this will help you in the coming weeks in differential equations when we start applying what we're doing with the second orders. Okay, so think about a damped harmonic motion. So now we have to have our amplitude dying out. So in this situation, the easiest way to do that, let me just write this up real quick. Is instead of it just being a cosine, we'll still have our A, which will be like our initial amplitude. But there's also going to be some sort of a e to the negative RT. I'll explain what that needs to look like in a second. but that's going to end up multiplying by our cosine of omega t plus phi. So let me show you what that means graphically. So this is going to be a graph. Horizontal axis is going to be time, and the vertical axis is going to be displacement. So I know it's weird to call that an x, but we're going to call it an x. Okay, so what we're going to see, we're going to start with a max, and then we're going to go down to a min, and then we're going to come back up to another max and another min and another max, but it's going to kind of die out like that. If you were to kind of look at those maxima and kind of connect the dots, you get a curve. Same thing if you look at the minima, you get a curve that does something like this. Well, this is that e to the minus RT. We'll even attach the A onto it. So you can kind of think of all of this. That's your amplitude. So your amplitude is decreasing exponentially, which means as time goes on, that'll eventually die out. So I call this an envelope function, because it kind of holds the function and it shows how the amplitude is changing. Now, obviously, the more damped the oscillation, the faster this will decrease. If you look at this form, you can see that to get a fast decrease, we're going to need a bigger R. So the bigger the R, the more quickly that motion gets damped. The smaller R, the longer it takes. So like with that spring that I was showing you, it's going to have a pretty small R because it kept its oscillation pretty well. As it was bouncing up and down, it didn't lose a lot of vertical. If you wanted to have a big R, we could put that in like honey, right? Put a spring in honey, you're going to see that it gets damped pretty fast. Okay, so in terms of how much it gets damped, it really depends upon that friction. And normally we look at that resistance as being proportional to velocity. Again, Ian kind of saw this when we were doing Diffie Qs the other day. But now we're going to allow for having position in there as well. And it's going to turn into just a second order. And again, because we just talked about it today, remember that third case? We saw that we didn't just get cosine or sine, but we could have an E as well. Kind of remember that, Ian? Watch, he's not even there. I don't think Ian's here right now. Well, anyway, so he's sleeping. But anyway, when you solve differential equations, you'll see that you can get an exponential piece as well. In this case, it's going to give us a negative R. Now, that R, it depends on two things. It depends on the mass. So it depends on what mass object we've got going, because that affects the gravitational acceleration or gravitational force. And then it also depends on the fluid itself, or whatever it is that's creating the dampening force. And that one, it really just depends on the situation.
So that AE to the negative RT, that's exponential decay, correct?
Correct. Correct. So the amplitude is decaying exponentially. All right, so in terms of the frequency, the angular frequency changes a little bit. When we do this, we no longer get omega is just equal to the square root of k over m. What we find here is that omega is now equal to the square root of k over m minus, excuse me, well, the way I've got it is minus r squared. So whatever that r is for that decay rate, omega has now been affected by that. So you may remember that in the absence of air resistance, this little spring kind of, I'm doing it for a spring. You could do the same thing if it was a pendulum or whatnot. But you notice that when it was just a spring with no air resistance, no friction loss or anything, we got omega was just equal to the square root of km. Now it's going to be decreased a little bit. The bigger r is, the more omega gets affected, which should again kind of make sense. Because remember, small r means, oh, we're slowly losing our energy. So we shouldn't expect that the motion, and in this case, the angular frequency, shouldn't really change that much. The bigger the r, the faster we drop it down, we'll see that that omega gets affected greatly. And so really, depending upon how the relationship is between Km and R, we talk about being underdamped, overdamped, critically damped. Don't worry about those terms right now. That's more of a mathematical thing that we concern about. But this is what happens when we have damped motion.
Does this function approach an asymptote, or does it go to zero?
Well, yes. The answer to both of those is yes. It approaches zero, which is the asymptote.
Mm-hmm.
It is one that will go above and below the asymptote, right? It'll keep bouncing back and forth above it, but long term it approaches that line. And horizontal asymptotes you can cross. That's totally fine. It's vertical ones you can't. So it does approach an asymptote, and that asymptote is zero. Because eventually, think long term, where's that spring going to end up?
Back at equilibrium.
Yeah, it's going to return back to where it started. So that's why we should see this approach zero as we go to infinity. Okay, so this is damped oscillation. So what about if we force this? What if we apply some sort of a force and have forced oscillation? Well, there are a lot of ways that that can happen, but the most interesting one is when that forced oscillation, that force that's helping out, is occurring at the same frequency as the natural frequency of the system. So what I mean by that, so think about this. We've got a function, say x is equal to a cosine of omega t plus b. But what we're going to do is, let's say that we apply a force that's going to be either sine or cosine. So I'm just going to make it sine of omega t. Let me actually give a different, it doesn't have to be just one, it could be b sine omega t. So this force has the same angular frequency as the natural oscillation, but basically we're going to target this so that we're going at exactly the same frequency. Okay, well, again, I'm not going to show you the numbers on this because it requires differential equations and you're not quite there yet. But if you do this, what you see is that the amplitude actually can increase. And so instead of what we saw before, which was this oscillation that just dropped off, now we can get this oscillation that builds. The term for this, and you've probably heard this term, it's called resonance. And again, we're just applying a force that's at the just right exact frequency to cause our amplitude to increase. Okay, so some examples of that. Let me switch screens. All right, so places where you see this. One is with musical instruments. Musical instruments, like think about a guitar. So a guitar's got that nice hollow sound chamber there. You pluck your string. What happens is the waves get in there and they build upon each other and they vibrate. The string is already vibrating with simple harmonic motion, but this resonance builds on that. It creates a larger amplitude. Larger amplitude in that case means louder, and so you can hear it better, right? Like if you were to pluck a guitar string that had the same tension and everything, but not have that big sounding container or shape, whatever, it wouldn't be loud. Like, I don't know if anybody's got an electric guitar, or if you've heard an electric guitar played when it's not plugged in, you can barely hear anything. That's because there's no resonance going on. Another place you can see this, I don't know if you've ever taken your finger, put it in a glass of water, and then like rubbed around the top of the glass, right? You all done that before?
Yeah.
And if you can get it just going at just the right speed, it starts to sing to you, right? It starts to actually produce a sound. Well, what you're doing, you're finding exactly the same speed as that natural frequency for that glass. You're applying a force that's basically building up that amplitude until it gets large enough that you can hear it. What's really going on, if you were to look at the side of the glass, so this is our glass maybe from the top, and you were just to look at this edge is actually vibrating up and down. That's the simple harmonic motion that you're getting. And so you're actually making the glass do this by rubbing it at exactly the right frequency. Now, if you kept going, eventually this would get so big that it would shatter. And that's what you see, like when you'll see somebody like an opera singer hit that really high note and hold it, and then you'll see the glass break. Now, a lot of times that's just movie magic, but it is a thing, like it can happen. And basically what's going on is you're increasing the amplitude so much that it overcomes the structural integrity of the glass, right? So if you've ever made a glass sing, you were doing a forced oscillation. But probably the best and most classic example is the Tacoma Narrows Bridge. We called it Galloping Gertie. You've probably seen videos of this. It was from the 1940s. It's a place out in Washington State where there was a bridge that goes over just a little waterway in the Puget Sound. But the wind was blowing it just the right way to create a forced oscillation that made that bridge start to sway side to side. As the wind kept blowing, it made that amplitude of the sway increase until eventually it couldn't hold anymore and collapsed. So I don't know if you've ever seen that video. I didn't pull one up, so I'm not going to waste our time by trying to find it and share my screen. But just do a YouTube search of Tacoma Narrows Bridge. Let me just put it in the chat window here if you want to look for it. So Tacoma Narrows.
That's also like what happens with the bowls that you have the like stick and you hit it and then you like go around it, right? It's basically the same idea as the cup.
Yep. Yeah, exactly. There are those I know they're used for like meditation and stuff.
Yeah.
They're also, I think they're called like water dancing bowls, where if you put water in them
Oh yeah, that's
and you
true.
vibrate just the right way, the water will start dancing and stuff like that. So that's exactly the same thing. Yep.
And it's cool when you have like water. I think it also happens with like I think what it was, they had like speakers underneath something, and then they have sand, and the way they vibrate will create different patterns with the sand. And I think that
Yep.
was pretty cool.
Yeah, and we'll talk a lot about that when we get to waves, specifically sound waves, because those are what we call standing waves. And
oh yeah, I've heard of that. Yeah.
yeah, and we'll totally see how those build, what makes them happen, and you know, what the conditions are. But it's the same kind of idea where you're taking this wave and you're building upon itself. That one, it's a little bit different because it won't grow to a huge amplitude because it's kind of controlled by the waves themselves, but you do get some interesting patterns.
Cool.
So anyway, so there's oscillations, and you know, we did this in one day because there's not a lot to it other than the fact that they all have the same structure, but we're going to use this going forward. Just realize that anytime you've got acceleration that's proportional to your position, but in the opposite direction, it will be simple harmonic motion. And there are lots of situations where we get that. And it's really nice because once we're there, we've got the model to describe it. We don't have to do anything new. We just have to realize that maybe the omega is coming from different quantities, right? Like we saw in the circle, the omega was coming from just the period of the spin, where with the spring, it was K and M, and with the pendulum, it was G and L, right? So, but beyond that, they all behave exactly the same way. All right. Okay, so let's talk, we got a little bit of time left. Let's talk about the exam that's coming up on Friday. But before we go there, just any other last questions on oscillations and harmonic motion?
Can sound travel through space?
No. Sound cannot travel through space because it needs some sort of a medium, because sound is what we call a pressure wave. So there has to be some sort of material to move for sound to progress. So sound does not happen in space, as opposed to light. Light does travel through space because it's a different kind of wave. So, and we'll talk plenty about that later. So like in Alien, when they say, you know, in space, no one can hear you scream, it's very true.
Well, I think just a question. Maybe I guess, I don't know. Sound doesn't actually exist. It only exists because we can process it, right? Like sound is just the waves, but then the way we interpret it is sound. I don't know if that's correct. I guess it does exist because we do hear it.
Yes.
But,
okay. So there is something physical behind sound. So I would argue that it does exist, as opposed to other things like a rainbow. I would say doesn't exist because there isn't anything physically there. It's just it's an interpretation thing. But sound's not just interpretation. It is a vibration. Sound is a vibration. So it's harmonic motion. And yes, you're right. Like our ear, well, specifically the nerves in there read the vibrations on the eardrum and interpret that as sound. And then our brain puts it all together, and right, and that's how we hear. So I would say that it definitely exists because it is a wave. It's caused by vibration and the, you know, back and forth motion of matter. It's not physical like a bottle that I can pick up or anything like that, but I would say it definitely exists. But our interpretation of sound could be very different. Like what you hear and what I hear may not be the same.
Yeah.
Because just how our brains are interpreting that same information. Just like, I don't know if you've ever had this thought experiment. So you look at my water bottle that's got some random beverage in it, right? And I ask you what color it is. You all are going to say something like pinkish, reddish, right? Maybe
Yeah.
purple, whatever. But okay, so like let's say I tell you, think of the color pink. You guys all think of what pink looks like. You all have an idea. If I were to put a bunch of stuff out and I said point to the pink one, you'd all point to the same one. Because we all have an understanding what pink is, but your pink may not actually be what my pink looks like. You might actually see that as something that I would call blue. Just because we're interpreting those waves, that information differently. It's kind of a trippy thing to think about, and
Yeah,
we'll never know.
I do like that idea because I feel like since pretty much everything that we see, we can't get out of our brains. So it's like everything that we see or we hear or we touch or whatever, it's all just like being like interpreted in our brains. But I feel like if we were to get out of our brains and somehow see the things the way they really are, it would probably like maybe be different, you know?
Yeah. Oh, for sure. And that would be incredibly interesting.
Yeah.
To be able to, you know, like you could put yourself up in here and see how my brain interprets stuff. And you might go, oh my God, that's completely different than me.
Yeah.
But we'll never know. We'll never, ever know because you can't do that. Right. Well, until we figure out some sort of brain transference thing and then start doing Frankenstein monsters and whatnot. But barring that, you know, we don't know.
Yeah, some trippy shit.
It definitely is. And I like when physics starts falling into the philosophy realm because it's and I think I've told you guys this before. My opinion is that science is just philosophy in a different side of the coin. Just trying to do the same thing, trying to explain existence. And you know, we just tend to use lots of numbers, where in philosophy they use lots of words. So. All right, well, let's talk a little bit about this exam and what you should expect and all that. So first of all, in terms of content, so it's going to start with momentum, and it's going to go all the way through gravity. I'm not going to put fluids on there. Okay, so it's just going to go through gravity. So I think that's chapter 13. Don't quote me on that. So I think it's chapters 9 through 13. So what that will have. So chapter 9, that was momentum. So conservation of momentum, impulse, collisions, things like that. Okay, so that was chapter 9. And then the next couple of chapters were about rotation. So all the rotation stuff will be on there. So knowing, you know, alpha and omega, being able to compare angular to linear quantities, to calculate moments of inertia, torque. So then also conservation of angular momentum. So all of those things, which they play out exactly like the linear quantities, right? All the relationships between them are the same, but instead of F equals MA, we've got torque equals I alpha, and, you know, and down and down and down the list. So the structures are all the same. We just have to apply them to the different situations. So know your rotational kinetic energy, know your, you know, like I said, moments of inertia, torque, be able to balance stuff out, look at how the different forces cause rotation and whatnot. So there's all the rotation stuff. Then there's equilibrium. And equilibrium, now we really just turn our attention to not just balancing forces, but balancing torques. So both of those have to happen. So also in that chapter, though, we talked about the different stress and strains, right? Whether we're talking about tensile, compressive, shear, bulk, so volume stuff. But those are always the same, right? We always look at the ratio of the stress and the strain. And remember that those things are, we're looking at force per area. right? It's not just a matter of how much force, but we kind of scale it for over how much area. And then the same thing with the deformation. We look at not just how much it deformed, but relative to what we started with. So it's that change in length over length, or, like in the case of shear, we're looking at sort of an angle kind of deal. But it's never just an amount when we're talking deformation. It's the amount over the original. So that was that chapter. And then we hit gravity. And the big things about gravity is being able to actually compute gravity between different bodies. Remember the formula for gravity, the G times M1, M2 over R squared. So be able to calculate that and figure out things like where we get points of equal gravity and the like. And then we also talked about escape velocity, which would be the velocity we need to get away when we're a certain distance away from the object. But realize that all those conversations that didn't take any other forces into account. So it's not really applicable to, say, being on Earth, because we do have things like the air resistance, friction that we got to overcome, and all that. But yeah, so that's what it's going to cover. In terms of the format, you should expect it to be similar to the quizzes, just more, right? The quizzes are probably good examples to start with in terms of problems. How easy or hard they are. I never try to make them super hard. I never try to make them hard. I know that they sometimes do end up being difficult, but that's hard to tell because it's a person by person thing. There should be a couple that are challenging because, I like to put on what I call the A-B separators. A students get them, B students don't. Ones that make you think a little bit. In terms of like note cards and all that, this is going to be a take home, basically kind of like what you guys did with the quiz. I'm going to turn it on. I'm going to turn it on at 3 o'clock, and you'll have until 5:30 to get it back to me. So that's 2 hours for the exam, and then 30 more minutes for, issues. If you're one of the people that has different testing arrangements, just message me and we'll figure out how to do that, like if you need more time and all that. So extra credit quiz question. No, there are no extra credit questions. It was funny, my DiffyQs class, somebody asked how come I didn't put those on, and I said, are you taking calculus right now? They said no. Well, because those are the bonus questions that have nothing to do with calculus. So yeah, so no extra credit quiz questions. They're just going to be what they are. So the other thing, though, that you should probably be ready for, because I do this when I give physics exams, is I'll ask you conceptual questions. So these are ones that aren't necessarily things that you calculate a number for, but just getting at the ideas. So think like the homework sets. Remember how there's always a couple questions at the beginning that are things like, for example, in that first homework set, there was something about, can a particle have momentum even though the system has momentum of 0 or something like that? And you basically just will answer that with a couple of sentences explaining your thought process. So get ready for those. So Ralph, you just said, can I put some bonus fun facts at the end? Maybe, if I think about it. In terms of how many conceptual questions, no clue. I have no idea how long this exam will be. Clearly, I haven't written it yet. That will be tomorrow, one of tomorrow's jobs. So I don't know, but there'll be a few. But obviously way more actually do the calculation and all that. But I do want to see your thought process on things. And that's what the conceptual questions can get at. So be ready for that. Be ready for things where you don't actually calculate numbers. So make sure you understand what's going on, not just how to run a formula.
So you said your DiffyQ class doesn't get bonus questions that have nothing to do with calculus?
Nope.
But isn't differential equations solving derivatives?
Yeah, but it's not calculus class. It's differential equations class.
But differential equations have calculus in them.
Right, but the title of the class is differential equations.
Oh, wow.
Well, I can't do those kind of questions on this exam the way that we're doing things this quarter anyway. Because, I mean, y'all are just going to go to Google. So, where's the fun in that? Unless I make them questions about me specifically, which, could be fun. How close of attention have you paid to me over the quarters in terms of who I am and what I like and all that? I'm not going to do that.
So I have a question for you.
Victor just said, I like cosine. Yes, that is true. If I said, what's my favorite function of all time? If you don't put cosine, then you're doing something wrong. So anyway, go ahead, Bradley.
What's your favorite well, I guess has calculus in it class to teach?
So my
I know you like teaching trig, but like not trig based calculus.
Okay, so with the exception of the calculus sequence and trig, what's my favorite class to teach?
Yeah, like what's your favorite math class to teach that's not trig?
Well, the one that's not trig would be Calc 1. But if I don't get the Calc class, I'd say linear algebra. That one's a lot of fun. But I like modern physics more. So. All right, so I guess you guys are feeling okay. Well, don't forget you can reach out to me. I'm accessible via email messaging and all that. I will get a lot of your stuff graded. My goal is to have everything through chapter 13 graded by early tomorrow afternoon. We'll see how that goes because it takes longer than normal. But I'm just about done with the first chapter. A lot of you probably already have scores, maybe not all of you. But I'm going to try to get through all that just so you can see my comments. But I guess other than that, have a great couple of days. And I won't necessarily see you on Friday, but I will be accessible even during exam time. So if you have questions that come up, feel free to send me a message or an email or something. And I should get back to you pretty quickly because my intention is to be near my computer that whole time. Okay. So, which means I guess I'll really see you guys on Monday. So have an awesome week and I will see you guys on Monday.
Thanks, Bruce.
See ya.
Have a
All
good
right.
day.
See you guys. You're welcome.